Hello and welcome to another episode of the Envisioneering Exchange, the podcast where industry leaders discuss the most important topics in building and urban efficiency. I'm your host, John Sheff, Danfoss's Director of Public and Industry Affairs, and you can subscribe to our show on Apple Podcasts, Spotify, SoundCloud, or wherever it is you get your podcasts. Today's topic is data center cooling technology, and I am really excited to be joined by Keith Dunnavant today. Keith is a PE and an ASHRAE Fellow and serves as VP of Data Center Sales for the Americas for Munters, a global leader in energy-efficient air treatment and climate solutions. He has more than 20 years of experience in data center cooling technology. Keith, welcome to the show.
Thank you, John. Very glad to be on the show today.
So Keith, it's really interesting that you started off kind of as a generalist doing a lot of stuff, and now you're so focused on data centers. But backing up a little bit, I think we understand why data centers are so important. They're, of course, rapidly growing part of our economy and kind of their backbone of everything from e-commerce to corporate office to the military. But I think the cooling technology and why that's so important is less well understood. But just kind of basically, why is it so important to keep them cool?
Well, all semiconductors have operating limits on temperature. So they generate heat. You've got to reject that heat. And the temperature around the semiconductor impacts reliability, it impacts life expectancy, and it impacts performance. So all of the above are reasons why they have to be kept cool.
Yeah, so it really is about the performance of these data centers, really the performance of all the machines that we use. I mean, what are the key requirements for this cooling, and why is it such a demanding application?
Well, ASHRAE has a booklet now called the Thermal Guidelines for Data Processing Environments, and we're now in their 5th edition. It's been constantly updated. I think the first edition came out in only 2004, so that just shows how new this approach is. Prior to that, all of the different processors had their own requirements and everything, so it was very difficult for engineers to establish what they should be doing with the cooling equipment. So today, most data centers are supplied with air in a range of 64 to 80 degrees Fahrenheit and a relative humidity of the supply air to the servers less than 70% and greater than 10% relative humidity. And that has been on evolving as we learn more and as the server technology changes.
So yeah, the cooling technology really has to keep up with the server technology and the requirements there. It's really interesting. I mean, how has that cooling technology evolved since that time, since you really started working with data centers? And then what's the current state of data center technology right now?
Well, it's evolved substantially. So going back to the late 90s, it was referred to as computer room cooling primarily, and it was treated more like air conditioning. Cold air was delivered to a big room with a lot of servers without a lot of thought behind exactly how to operate this most efficiently. So 48, 50, 55 degree air was delivered, and it wasn't very efficient. They did use economizers, but there was a whole lot of compressor use back at that time. About 2008, a game-changing idea was applied, which sounds obvious now, which is hot aisle containment or cold aisle containment, however you want to refer to it. And that is containing the heat that's discharged out of the back of the servers into a contained hot aisle and allowing that to flow up into a plenum, usually back to the cooling units. And by containing that heat and not allowing it to recirculate back around to the front of the servers, you could then deliver more room neutral air, like 70 to 75 degrees, which allowed you to operate with a lot more economizing hours and much more efficiently. So big changes have evolved. And in terms of equipment changes, there's been a lot of new technologies, free cooling chillers, cooling within the racks themselves, often called in-row cooling, use of evaporative cooling, of both direct and indirect evaporative cooling technologies, et cetera. So many changes, and it continues to evolve.
So Keith, we talked a bit about why the requirements for data center cooling are so intense and also how the technology has evolved, but we didn't touch on why this is such a demanding application. So what about the application makes it so tough to deal with?
Well, it's a 24/7 mission critical operation. So it's got to be up and operating all the time. And it has to operate during extreme cold winter conditions, under the hottest summer conditions, under low load, part load conditions. When you start these data centers up, they may only have 10% of their intended full load capacity. And so you have to think through how the system's going to operate at that condition, as well as the full load condition. It's got to handle disruptions in utility power where the backup generators kick on and transfer switches flip over and the cooling units are again powered up, and they have to start very rapidly because the servers have had their power all the time. They're connected to a UPS, an uninterruptible power supply, generating that heat all the time. So you've got to get your cooling units up quickly. And you've also got to think through all the possible weather scenarios, et cetera, and make sure your control strategies address all of those, all while trying to operate most energy efficiently all the time. So that's kind of what makes it a demanding application.
Yeah, I can understand why it's so demanding and all of the different inputs that are coming in. I mean, what trends are you seeing in data center cooling today? Where is the industry going right now?
Well, the industry today is still primarily cooling data centers with air. So it's primarily an air-cooled environment, and it's also trending towards not using water, or if they are using water, to use as little as possible. Hyperscalers tend to still use water, but sparingly, using direct evaporative cooling technologies and using ambient air and letting the ambient conditions that go to the servers float to some pretty high extremes before the evaporative component is actually brought online. Other trends, there's obviously been a focus on energy efficiency, including peak connected power, which drives the generator sizing, but there is still a definite interest in initial cost, and sometimes that even trumps total cost of ownership due to financial goals that the companies may have. There's been a trend towards using more air-cooled chillers and chilled water crawl units, which is why Munters introduced a product last year called SciCool to compete with those air-cooled chillers and offer some benefits in terms of efficiency and modularity, et cetera. Also trends towards, we're seeing a lot of stress in our sourcing. So metal prices have been going up and control components have been hard to get. So definitely everyone in the supply chain has had more focus on developing strategic partnerships, et cetera, to try to smooth some of that out.
Yeah, I think everybody's feeling some supply chain pain right now. But you touched on a couple things I kind of want to go back to. You mentioned use of water and energy, and I think we've all seen some of these data centers in the news around energy use, Bitcoin mining, stuff like that uses. Explain why they consume so much energy, and then what Munters is doing to address efficiency. And then, secondarily, what does sustainability mean in the context of data centers? And you mentioned moving away from water. That is a big concern, though.
It is a big concern. So you hit on a lot of questions there. I'll try to hit them, starting with the first question. Why did data centers use so much energy? Well, first, compute power, all the CPUs and GPUs on all these servers is very high. And in addition, all of the power that goes to those servers results in heat that has to be removed. So every kilowatt of power that goes to a server that's consumed by a server also comes out the back as heat that has to be removed, which is additional electricity that has to be expended to reject that heat. And that can be, on the hottest summer days, up to 40 to even 50% of the IT power. So all of that ties in. And so there's metrics that we in the industry use to establish how efficient you operate. And one of those is called the power usage effectiveness, which is the IT power plus the cooling power is the biggest part of it anyway. There are more components, but divided by the IT power. So if you have a power usage effectiveness of 1.1, that tells you that your cooling is using 10% of the power of your IT load. So that would be a pretty efficient data center. And that's a lot of the modern hyperscale data centers hit those kinds of metrics and even better, which also translates to what we call in the industry a coefficient of performance of the cooling system of about 10. And I think you had another question about water.
Yeah, we were talking about water usage and kind of moving away from water usage and then segueing that into sustainability mean in the context of data centers.
Yeah, so, if you're in the desert, water use is not something that you want to be reliant on because it's not sustainable. If you're in eastern USA, in an area that you get plenty of rain and the reservoirs are high, or you can even collect rainwater and use it, then you can use water sustainably. But in terms of sustainability over the long haul, we have to move away from using fossil fuels to generate our power and towards more renewables, which the industry's already adopted, the solar and wind and hydroelectric power, et cetera. And I think our biggest hurdle going forward with that is going to be how to store that energy.
Yeah, we've talked a bunch on this show about those issues and storage and renewables and generating more electricity sustainably to power things like data centers. And you mentioned here a bunch of times the heat recovery, heat rejection. And we've talked about heat recovery on the show several times, but data centers do produce a lot of excess heat. Is there an opportunity to utilize that heat in other applications?
Absolutely. In fact, I've been surprised how slowly the adoption of heat recovery technologies has come into play. We've done one project where we extracted the heat and it is used for district heating. That's on a project over in Europe. But the opportunities are immense. We've got to change our mindset, though. We have to have data centers connected to indoor swimming pools and greenhouses and beside malls in northern climates that need that heat all during the winter months, et cetera. So there's a lot of potential, but it hasn't really been adopted widely yet, though.
Yeah, I think there is a lot of potential, particularly as we see more heat pump applications for heating and for cooling. I think there's opportunities there to connect buildings and create more district loops, but that's a topic for another show. Data centers seem to be increasing in size. You see these huge farms now. What do these larger facilities mean for HVAC? And are the current cooling technologies capable of keeping up with that type of demand? Are we going to see new technologies to meet these larger size data centers?
Well, the most important thing to remember is that the only place that you can reject the heat is to the atmosphere if you're building your data center on land. That's why some folks have looked at using seawater, et cetera. And so what does that mean? That means that if all of the heat is being rejected to the atmosphere, you can only have so much kilowatts of heat produced within the building because you're limited on how much space that the cooling equipment takes to impart that heat into the ambient air and reject it. And so that's a limiting factor. And that's why the big data centers that are out there today are typically only 1 to 2 stories. There are some multi-story data centers, but you have to be very creative in how you're going to reject the heat because there's only so much roof space. Or if you don't put the cooling equipment on the roof, you've got a lot of real estate all around the perimeter that's being used to house all of that cooling equipment. So, and in terms of your question, do we have the technologies to cool them? We do currently. I do think that the trend may be over time actually allowing the data centers to get smaller because there will be a shift towards more liquid cooling, which will allow you to have a lot more density of IT in the room and still reject it effectively using various forms of liquid cooling.
I mean, that's interesting. So you're saying the future, we could go back to these more, what we're calling edge data centers, smaller centers that are not as centrally located, and we could go back to more liquid cooling to make those centers as efficient as possible, as dense as possible in terms of the IT.
Yeah, I think liquid cooling makes sense probably for edge, depending on the capacity, et cetera. And I think it's going to make sense for the hyperscalers eventually. I've been wrong on this before. I've sure expected that we would have adopted more liquid cooling by now because it just makes so much sense. But this industry, while it's high tech and things are constantly evolving, it tends to move slowly in terms of certain changes. So we'll see.
We'll see. You hit on something that's really interesting, putting these data centers, underwater or in very cold locations. I mean, you need to have the data centers located near to markets they're serving, but are these extremes really necessary? We're going to keep seeing this in some of these very cold locations, or even, like you mentioned, underwater?
I think the underwater is interesting. I will be very surprised if that is a strategy that gets widely adopted over time for various reasons of serviceability, et cetera. But in terms of putting data centers in cold climates, certainly that makes sense from a cooling perspective. We're not seeing a lot of that, though. We're seeing more to what you said earlier. They're putting data centers where they have demand. And so that's every place.
Yeah, basically. Well, we're coming to the end of our conversation. We like to end these shows with a forward-looking question. We've talked a bit about the future, but how do you see this market evolving in the next 10 years, and how is Munters specifically preparing for that future?
I think that we're going to see more liquid cooling. I think it eventually will be the dominant strategy. I think air cooling is going to continue to be a part of the cooling picture for easily the next 10 years. We didn't talk about the different kinds of liquid cooling, and there's immersion cooling, there's direct to chip, there's two-phase fluids that can be used either at the immersion level or direct to chip. So there's going to be an evolution in cooling technology that should be very exciting. Also, new computer chip technology. IBM announced last month a new 2-nanometer semiconductor that promises to use 75% lower energy compared to current 7-nanometer semiconductors. I don't know how long it will be before we see that, but that's certainly of note and a huge quantum leap in terms of energy efficiency. In terms of how Munters is preparing for the future, well, we have an R&D team that is working with the sales group, and we're listening to the customers and trying to meet their needs. So we're already looking at the liquid cooling piece using our SciCool technology, and we're really excited about that because when you can take refrigerant directly to chips or directly to immersion cooling pods, you get two-phase heat transfer, which is more efficient than circulating chilled water. So we think that's got really good potential. We're developing and enhancing our software to include predictive maintenance features that'll be in the future, developing more strategic partners to ensure our supply chain and production capacity. And the biggest thing, we've taken a huge step here in the last few months, is we announced that we're building a new factory. It's located near Roanoke, Virginia. So this will be our new center of excellence for data center cooling for the Munters portfolio.
Oh, that's awesome. I'd love to get down there sometime and take a look once it gets up and running.
Yeah, we're really excited about it. And also the test lab that allows us to validate performance of all of our new products and show it off to our customers.
Yeah, that's awesome. And I think that's so important. We have similar sites like that where we can test customer applications and let them come down there and take a look also. So all very exciting stuff. Keith, this was a great conversation. I learned so much. I just want to thank you for coming on the show.
You're very welcome.
Great. Well, that's it for this episode of the Envisioneering Exchange. Again, I'd like to thank my guest, Keith Dunnavant of Munters, for joining us. Don't forget to subscribe to Envisioneering Exchange on Apple Podcasts, Spotify, SoundCloud, or wherever it is you listen to your podcasts. And lastly, if you enjoyed this episode, please don't forget to rate, review, and share with your network. Thanks for listening. Again, my name is John Sheff. I'm Danfoss's Director of Public and Industry Affairs, and we'll talk to you next time.
This podcast is for information purposes only. The views, information, or opinions expressed during the Envisioneering Exchange podcast series are solely those of the individuals involved and not necessarily represent those of Danfoss LLC and its employees. Danfoss LLC is not responsible and does not verify for accuracy any of the information contained in the podcast series available for listening on this site. This podcast series does not constitute professional advice or services. This podcast, including Danfoss LLC and the producers, disclaim responsibility from any possible adverse effects of information contained herein. Opinions of guests are their own, and Danfoss LLC in this podcast does not endorse or accept responsibility of statements made by guests. This podcast does not make any representations or warranties about the guest qualifications or credibility. Individuals on this podcast may have a direct or indirect financial interest in products or services referred to herein. This podcast is available for private, non-commercial use only. You may not edit, modify, or redistribute this podcast. The developers of the Envisioneering Exchange podcast site assume no liability for any activities in connection with this podcast or for use of this podcast in connection with any other website, computer, or playing device.